and welcome to the Spring 2024 Summit Slides for VoltServer Acts. I would like to start this presentation by introducing our technical directors, Andre Costa, Zach Chofe, and Camilo Geraldo, and our team members, Andrew Brown, Daniel Bradley, Wesley Hardesky, and Brian Pivoinski. VoltServer, our sponsoring company, is located in East Greenwich, Rhode Island. They are innovators in the field of fault-managed power systems with their digital electricity technology, which can provide the delivery of power over long distances safely and efficiently, seeing applications in airports, stadiums, resorts, agriculture, and more. What motivates this project is VoltServer's need to certify cables for use with their digital electricity technology. This process consists of taking 100, 200, and 300-foot samples of cable and testing those, as well as combinations of samples up to 600 feet long. This is a long process that is currently done by a person that needs to switch cable lengths themselves. Our project intends to change that by automating the process so it can be done without someone tending to it. This would accelerate the testing process by allowing it to be run overnight and would allow VoltServer's employees to focus on our work. Our main focus for this project was to build an automatic system based around a LabJack controller using C# programs, which would allow for the system to be neatly integrated into VoltServer's current testing environment. Our solution uses a PCB that has traces on the internal layers, which correspond with the proper connections for each cable length, each connection being made between surface pads on the PCB. This PCB is rotated into the correct position for the connection via a stepper motor and is then pressed against input PCBs through the use of linear actuators which hold position to make the connection throughout the test.
Hello, my name is Wesley Hardesky, and I'm an electrical engineering major with a mathematics minor. Most of my technical contributions to this project involve mechanical prototyping and design to bring our ACT system to life. Some of my key accomplishments in this project involve figuring out how we're going to make this design work in the first place. Yes, we have the idea of a rotating PCB, but how are we going to make it rotate and lift in the first place? And how are we going to keep it stable? There's so many questions, and after countless ideas and sketches, I finally used SolidWorks to create a detailed mechanical system that will do exactly what we need our ACT system to do. Eventually, I began 3D printing and prototyping parts for the next step of testing and verification. Now, I'd like to talk a little bit about our system assembly here. So, in green, you can see our main PCB, in which VoltServer's DE signal will pass through. And this PCB will rotate from this DC stepper motor at the bottom on a square shaft. Now, we chose the shaft to be square because we need the PCB to slide up and down the shaft to make its connections to the input terminals at the top. But we also need the PCB to rotate from the motor too. And the square shaft was the only way we can accomplish this. Now you can see the 4 linear actuators that are sitting right on top of the motor, and they connect to a plate that houses the PCB and keeps it stable. Now, once our motor is at its desired rotation and our linear actuators are active, our PCB will rise up to the input terminals, making a secure connection, and VoltServer's DE signal will pass through our ACTs at its desired cable length. Now, there were 2 different versions of this prototype that we designed, and I'd like to start off by showing a view of our version A prototype that's split up and easier to comprehend and digest. So on the left hand side here you can see the bottom half with the PCB, the main PCB itself, along with the plate that rises and falls with the linear actuators along these 4 rails here. And then on the right hand side you can see the top half of it, which also sits on the same rails, and there are the 8 individual small PCBs. So these 8 individual small PCBs will go ahead and correspond to positive and negative 100 feet of cable, which will be connected as an input to our ACK system here. Positive and negative 200 feet of cable, positive and negative 300 feet of cable, and then finally positive and negative output that VoltServer will go ahead and connect their test equipment to collect all of this data for cable certification. Now on the right hand side with these 8 small PCBs, you can see the 8 PCBs are connected to one plate that is coupled by springs and connected to another plate which is attached to the rails. Now the reason that there are springs, there's 4 springs in between these 2 plates by the way, is so that when the main PCB comes up in contact with these small 8 PCBs, the springs kind of help ensure a smooth, more firm connection. And when the linear actuators are holding in place, the springs will also return a force, kind of just revalidating that connection. Now moving over and switching gears over to version B of our prototype, we kept the bottom half the same, except now this time we just changed the top half. So instead of 2 plates coupled by 4 different springs, we have these individual little smaller plates that are a little bit bigger than the actual PCBs themselves, and they are each coupled to the bigger plate connected to the rails with 2 springs. Now the reason we went ahead and made this prototype is because while testing the original one with only 4 springs and a bigger plate, we saw that some pins weren't connecting to the PCB all the way, and there were tiny little gaps causing some connection issues. So we figured if we come up with a way to make each one of these little 8 PCBs move more independently and more freely, they would be able to connect to the main PC better when the linear actuators are activated and the big PCB rises up to connect here.
My name is Andrew Brown, and I'm going to be talking about my individual contributions to the project, which mainly was composed of developing the PCBs that were used. So again, my key accomplishments were designing 2 of the boards that we used, the main rotating PCB and the set of contact PCBs, as well as selecting and soldering the contacts for the boards and all of the connectors for the wires. And also general testing, assembly, and calibration of the prototype. So this diagram here is meant to reiterate the general idea that we're going for. We have these 2 boards, one down below here, which is free to move around, and one that is fixed up top with these array of contacts. And we can do this rotation via a DC stepper motor, and depending on the orientation of the board with respect to the fixed contacts, that will select which inputs are being combined for any one of the given lengths that we want. So then once the board is in place, we can use a set of actuators to extend the board and complete the signal path for the duration of the testing. So now these figures are a little bit more indicative of what the board actually looks like. We have this large board with these arrays of contacts split up into 8 different sections for each of the inputs and outputs. And then within each of these sectors, we have 6 different pad arrays of 4 pads for each channel. So we have this board here with these green contacts meant to represent the fixed contacts above the rotating board. And then if we just apply a small rotation, you'll see that they get moved over one set of the pad arrays. So we go from this 100-foot here over to these 200-foot pads. And again, we can do this small rotation easily using a DC stepper motor. So this is what the board actually looks like. On the right is the picture from software. It was made in Altium Designer. And on the left, that's how the board came out. And the board on the left notably has these mounting holes to actually couple it with the shaft of the motor. That way we can rotate it as we like. These are the contact boards. There's 8 total. They're also made in Ultium. And we chose to have these spring-loaded contacts, which you can see in the top photo here. So we have these, there's these little pogo pins, this base part here, and these sort of, it's like a ballpoint pen with a spring in it. So they kind of decompress. That way we know that all of them are in contact with any of the pads. And then this is a top-down view where we have these holes where we can solder our inputs into, and the pogo pin or spring-loaded contacts in the center of each of these channels. And on the outside we have these countersunk holes, so that way we can actually screw them into our printed plate, and that way it sits flush, so they will make contact with the board without interfering with the actual spring-loaded contacts. So the assembly view, this is the whole system, and we have this plate on top, which were those fixed contact boards. So within each one of these little stilts here, there's one of those boards. This is only one angle, so you can see 3, but in total there's 8 of them, and they sit above the main board, which is sitting below. So then to kind of isolate that top part, you can see radially we have 8 of them spread out evenly, and again, that's just hovering above that main board that we previously saw. And integrated in the system, you can see on the left we have our inputs with each of these terminals coming out here, so they can just plug them into the cable farm at the office. And again, there's one pair for each of the inputs and outputs, from 100 all the way up to just the power and ground. And then on the inside, this is sort of a top-down view. You can see the whole assembly sitting in, and the wires come through to each one of those respective contact boards sitting above the main board.
Hello, my name is Brian Pivoinski, and I would like to go over some of my technical contributions to this project. My main focus was on motors and moving the main PCB. I looked into different motor types such as AC servos as well as brushed and brushless DC servos before settling on stepper motors due to their affordability and ease of use. Stepper motors are easy to implement due to the fact that they break up their rotation into a series of steps, usually 200 steps per full rotation. This unfortunately makes our desired rotation of 7.5 degrees not possible. In order to overcome this, I found a solution by using a motor driver capable of microstepping, which makes the motor capable of achieving more positions by breaking steps into smaller ones. The choice of stepper driver also allowed for an easy solution for controlling the motor with the lab jack, since it is based around the step direction interface. This interface requires only 2 signals, one to set the direction of rotation, and 1 pulse signal where each pulse represents a step to be taken. We also needed a method to move the main board up and down while applying equal pressure to all contact PCBs. This would require the use of linear actuators, which are traditionally pretty large, but we found a solution with these Accutonics PQ12 actuators. These actuators have a footprint roughly the size of 2 AA batteries side by side, but are capable of pushing with a peak force of 40 newtons. We used 4 of these to apply even pressure to our contact boards. These have their own motor driver and are controlled with a pulse width modulated signal from the lab jack. I would now really briefly like to go over how all of these components fit into our server rack enclosure, which you can see in this picture here. The white object at the lower center of the picture is our actuator array. It has our 4 actuators mounted inside of it, and it also has a mounting point for our encoder, which is the silver colored thing on top. The actuator array mounts to our stepper motor, which is the black block on the bottom. The red box is our lab jack, which we use to control everything. At the bottom we have a green board, which is the driver for the linear actuators, and to the right we have a signal splitter, which allows us to use 1 driver to control all 4 actuators. We mounted our stepper driver on the back wall of our cabinet since it is a bit larger. And above the stepper driver we have its 24 volt power supply as well as a 6 volt buck converter, which allows us to use a single power supply for both the stepper driver and the lower voltage actuator driver.
Hello, my name is Daniel Bradley, and I am here to talk to you about the control systems of the AX device. Now this involves both a desktop computer, which will be available on site, as well as the LabJack data acquisition device, which we used kind of like a microcontroller in this context. Now, the control system has several levels of abstraction. At its lowest level, it is the basic communication signals between the LabJack and our three components. This is a 3 millisecond pulse signal for the stepper motor, which will tell it how many steps to take, and a pulse width modulation signal to the linear actuators, and the width of that signal will determine how far for the linear actuator to extend. And then the rotary encoder uses SPI to send bytes back and forth, reading us the location, the rotational position of the PCB board. Now my responsibilities involved writing the low-level code which implemented these basic signals, as well as writing the sort of middle-level code which built upon those signals to implement the logic flow of the three components individually. Lastly, my job was to combine all three of these into a single comprehensive control flow, which would ultimately execute the ABOs asked of this project. Here's a diagram of the software dependencies that we ultimately ended up. We wrote about 6 classes to achieve our goals. At the bottom, you can see the two of the fundamental signals, that is PWM and SPI, which are implemented by their respective components. Step control does not have a lower level function, as it just used the basic 3 millisecond pulse signal I mentioned earlier. This wasn't really any kind of standardized signal that could be used on its own, so we ultimately decided just to keep it within the step control class. And then, as you can see at the top, ax.cs, that is our final main program, which does the entire control flow, and it implements each of the 3 devices in order to achieve that control flow pretty well. Now, I would like to look a bit more in depth at the control flow. To the right here, you can see our basic chart, our basic flow. When the program starts, it will begin with a 100-foot length test. And then when the test ends, it will prompt the user to start the next test, which will be 200. And it will go all the way through all 6 tests until the program ends. We have made sure, on top of this, to provide a robust library of functions at all levels of abstraction, as well as documenting all these functions very well, because we wanted to make sure that VoltServer would be able to change and modify. Like, this is our default that we are providing to them, but it is also highly customizable. It could be further automated, the order could be changed around, or it could be implemented in some entirely different way. If they so wished, we simply provided them the toolkit to achieve this goal. In the end, we are quite happy with our results. We found that the control system was able to properly implement everything and ultimately provided no problems for our system. On the project as a whole, as a team, we are definitely proud of the work we've achieved after 8 months of research, brainstorming, and designing, as well as lots of testing. We do think we can say that we achieved our ABOs. There certainly remains room for improvement. We have identified issues with our design, but we think that this is a very functional proof of concept, which can also serve as a great starting point for any future research within this area. We think that within the scope of a capstone project, that ultimately we achieved probably some of the best results that we could have gotten.